Inverse functions are functions that undo each other. The formal definition of an inverse, or how we verify inverses, is with function composition. So the definition of an inverse of a function: let f and g be two functions, so here's f and here's g, such that f of g of x is equal to x, and g of f of x is equal to x. Meaning, we will compose these functions both directions. And if both times you compose them, they end up simplifying down to x, just literally a plain x, then they are verified as inverses of each other. Inverse functions undo the other one, so you're going to have a lot of inverse operations. The opposite of addition is subtraction, multiplication is division, square is square rooting, and all of that good stuff. The notation that we use for the inverse of a function looks like f to the negative 1, but that's literally how you say f inverse. So f to the negative 1 is not like 1 over f, it's the inverse of f. That's how we're notating it. And then this sentence right here is pretty important. The domain of f is equal to the range of f inverse and vice versa. So your domain and your range switch, which means your x's and your y's switch. That's all that we're doing with these functions, is undoing them, switching the x's and y's. So let's start right away. We're going to verify that these functions are inverses. So I'm telling you they're inverses. We're going to verify. Here's f of x. Here's g of x. To verify that they're inverses, we're going to check both directions of composition. We'll start with f of g of x. What? I'll pause. Sorry, you're right. I'm going really fast. Y'all are finding highlighters, all that business. So we're composing it this direction. F of g of x. So what function do I put on the inside? G of x. So to follow kind of the notation I used last class, we're going to leave this f right here. We're going to take the g of x function and we're going to plug it in inside the f function. So that means anywhere in the f function that there is an x, I'm putting the purple function. I'm putting g. Therefore, I have 3 times x plus 2, but x is x minus 2 over 3. What happens when you multiply 3 by something that's divided by 3? They cancel out. So these 3's are going to cancel out. Okay, so then we have x minus 2 by itself, and then plus 2. Oh, minus 2 plus 2, what happens? Cancels out. So what is this equal to? That's a good start. We need both directions of composition, f of g of x and g of f of x, to equal x to confidently say that they're inverses of each other. So your turn. I want you to practice composition, and I want you to verify the other direction. You're doing g of f of x. I want you to do this one. Help me verify that these are inverses of each other. For this one, we're putting the f of x function inside the g of x function. We're composing them that direction. So I have g of x here, and inside g, I'm going to plug 3x plus 2 in. Okay, so what that looks like is, that's the shell, for lack of a better word, for the purple function, and where x is, I'm going to put 3x plus 2. And then, oh look, plus 2 minus 2, those cancel. And then I have 3x over 3, and oh look, those 3's cancel, and what am I left with? And if both directions for composition, f of g of x and g of f of x, become x when you're done simplifying, that's how you verify that they are inverses of each other. Make sense? That's verifying an inverse. We also need to be able to just find the inverse of a function. And for the most part, this is real easy. Here are the steps. Number 1, replace f of x with y in the equation for f of x, if necessary. Sometimes it already says f of x, but if it says y, put an f of x there. This is the key right here. You're going to interchange x and y, and that's a really fancy way of saying switch the x and y. You're going to switch their places, and then you're going to resolve the equation for y. If it makes a good function, meaning it passes the vertical line test, f has an inverse function, you would replace y with f inverse, and then we can verify our result the same way. Can we try it? Because it's really simple. Number A, finding the inverse. It already says f of x, so we can put a y there just to make x's and y's easier to switch. So this is y equal to 7x minus 5. We're going to switch the x's and y's. So literally just replace every x with y and every y with x. See how I just switched their spot? But now we want to solve for y. I want to get the y by itself again. How do I start getting the y by itself? Plus 5. So I'm going to add 5 to both sides. And then what? Divided by 7. So if I do x plus 5 over 7, that's going to be equal to y, which means, to make it look fancy, we say f inverse, or the inverse function of f, is x over 5. X plus 5 over 7. You just make it look nice and tidy at the end with the fancy function notation. Oh, that's the symbol for inverse. So f inverse, that's what this is, yeah. Yeah, so these two functions are inverses of each other, and we could verify it the way we did up top if we wanted to. Can you guys try one? You got it. Same thing for B. This time it's going to be called G and G inverse, just FYI. We still start by just replacing g of x with y and then switch their spots and then solve for y. Everybody's so nervous when you try one on your own. Okay, here's what I would have done for this one. I would have switched g of x with y, just so I have x's and y showing. I'm going to switch the locations of x's and y's. So then this becomes x equal to y cubed plus 1. I start solving. So I subtract 1. And then how do you get rid of a cube? You cube root it. So I'm going to cube root both sides, and I have x cube root of x minus 1 equal to y. Once y is isolated and we have an actual function, and cube root is a function, that works, we say that g inverse of x is equal to the cube root of x minus 1. Voila. No, because we would have a restriction if this was a square root. A cube root is actually defined everywhere. It doesn't have a restriction on its domain, but if it was a square root, we would have to give it a domain restriction. Good call. Can we try another one? I will say this one's a little bit more difficult because it just requires a little bit different kind of algebra. So if there's a question on these two before I flip it over, let's ask. Are we okay? Algebra steps, we're fine. Let's do some crazy algebra. You ready? Woohoo! Let's find the inverse of f of x equal to this rational function x plus 2 over x minus 3, where x cannot equal 3. Cool, we took care of our domain. Same thing like before. I am going to replace f of x with y. Then I'm going to switch every x to a y and every y to an x. So I have x equal to y plus 2 over y minus 3. So far, so good? We replace f of x with y. We switch the x's and the y's. Now it gets to be the fun part. We need to solve for y. This is where it gets crazy. Because you see two separate y's on a top and on a bottom, we're going to have to do a lot of algebra to get it to one y on one side of an equation. The first thing we're going to do is we're going to multiply both sides by the denominator. So I'm going to multiply y minus 3 on both sides. Why am I doing that, you ask? Great question. Thank you for asking. It's going to eliminate this factor on top and bottom. So now, if I rewrite my problem, I can rewrite the left side of this equation as yx minus 3x equal to y plus 2. We still have two separate y's, but they're now on the same level. A second ago, there was one in the numerator, one in the denominator, so I took care of that, and I got them all in the numerators. Let's put all of the y's on the same side and all of the x's on the other side. So I'm going to subtract y from both sides. I'm going to add 3x to both sides. I basically flip-flop those two terms. I moved this term this way, made it positive, and I moved this one this way, made it negative. Now, there's still two y's. They're both on the same level, and now they're on the same side. Now I can factor out a y. If we look just at this side, doesn't this term and this term both have a y in them? Reverse distribution, we're going to take that y out. We'd be left with x minus 1. Pause and quick check. All I did was divide this term by y, the y's cancel, and this term by y, the y's cancel. But the y's still chilling in front. We can't just let it go. We are one step away from getting y by itself, because right now y is multiplied by this entire parentheses. So we divide it by that entire parentheses. We'd end up with y equal to 3x plus 2 divided by x minus 1. Then to make it look fancy, we say this is f inverse of x equal to 3x plus 2 over x minus 1. But there's a number we cannot plug into this function. What is the number we cannot plug in? 1. We cannot use 1. We have to include those restrictions on this domain. Let's walk back through those steps, so maybe you can write down words next to each step, so you're not just looking at this math and going, what did we do here? I'm not going to write down the words, but you can if it's helpful. What did we do from the question printed on the paper to this step? Yeah, put a y instead of f of x. What about the next step? Switch the x's and y's. What did I do in green here? Correct. I multiplied by the denominator because we want all of the y's on the same level, essentially. All in the numerators. Now I did like a whole bunch of stuff at once from here. Not only did I multiply by the green, how did I get this? I distributed. Okay. The next step, what did we do again? Put all the y's on the same side and everything else on the other. I did two little algebra moves at the same time. What is this called when we do from this step to this step? Reverse distribution, called factoring, but reverse distribution is great. And last but not least, divide. If you're writing down some words, that might be helpful words to see. Then we make it fancy with the notation and include our restrictions that x cannot be 1. Questions, comments, concerns about this kind of question? I know for sure there are some of these on your homeworks for this one, and I know for sure there's one of these on the chapter test because I just looked at it. So are there any major questions we want to ask before we bypass this? Okay, so do you remember when we learned in like chapter 1.1 or 2.1 or 2.2 about the vertical line test? And I told some of you who answered to me on our quiz that if you said it passed or didn't pass the line test that I'd accept it for now. Here's when I will no longer accept it because now we have a different line test. We're going to have a horizontal line test, the HLT. And the horizontal line test tells me when functions are what are called one-to-one functions. A horizontal line test is literally a horizontal line test. The same way a vertical line test works, this time it's just horizontal. The horizontal line test tells me whether a function f has an inverse that is also a function. So if I was doing the horizontal line test here, and I was trying all of these horizontal lines, do any of these horizontal lines touch this graph more than once? No. So what we conclude is not necessarily that this is a function, although that it is. We would know that the inverse of this is a function. So the horizontal line test doesn't tell me about the function, it tells me about the inverse of the function being a function.
So if it doesn't go through twice, the inverse is a function?
The inverse is a function.
Which is opposite.
Correct. What about this? What's happening here? Will this one have an inverse that is a function? No. So f inverse is not a function. It's just a relation. That is what the horizontal line test tells me. Not necessarily about the function, but about the inverse of the function. Does graph C have an inverse that is a function? No, because there's this point right here where it crosses 3 times. So we would say f inverse is not a function. What about D? Does it pass the vertical or the horizontal line test? Yeah, I cannot draw a horizontal line that crosses this graph more than once, so we know that f inverse is a function. So again, that's what the horizontal line test tells me. Not whether the function is a function, but whether its inverse is a function, which is a whole lot of the word function rolling around. But that's the HLT. So we have to specify which line test we're using now because there are different line tests. Vertical line test tells me if mine is a function. HLT tells me if its inverse is a function. But these HLT passing graphs, if it passes the horizontal line test, it is also, like I said earlier, called a one-to-one function. A one-to-one function is just the mathematical name for something that is a function and whose function is a function. Basically, there are no x values that give you different y values. It only has unique inputs mapped to unique outputs. That's a order. Like the sentences all on here repeat the same thing over and over again. But basically, a one-to-one function will pass both the VLT and the HLT. That is a one-to-one function. It's a function, and its inverse is a function. It's called a one-to-one function. Every x has a different y. No x's repeat, no y's repeat, is basically what it's saying. Now, these one-to-one functions, because they don't have any repeating x's and y's, we can find graphs. Oh, why is it not white in the background? There we go. We can find values of them very easily on a graph because we can just reflect these things over a diagonal line since there's no repeating happening, and we can just switch the x's and y's. So there is a relationship between the graph of a one-to-one function and its inverse, because inverse functions have ordered pairs with the coordinates interchanged. If the point a comma b is on the graph of f, then the point b comma a is on the graph of its inverse. You see how they just switch spots? These 2 points, a comma b and b comma a, are symmetric with respect to the line y equal to x. So we're going to have this diagonal dashed line across our screen here where all of the graphs are foldable. You can fold along this diagonal line and one dot will land on top of another. So let's graph some inverse functions. We're going to use the graph of f to draw the graph of its inverse function. All we have to do, my friends, is flip-flop the x's and y's. So if this dot on f appears at -3, -2, where will it appear on f inverse? -2 and -3. So I go to -2 and then -3. This is going to be the first coordinate point for my f inverse. -2, -3. We just flip-flop those. That middle point occurs at -1, 0. Where does it appear on the inverse? 0, -1. So here's 0, -1. Then we have 4, 2. Where do I put that dot for my inverse? 2, 4. And then I can play connect the dots. So we'd have a graph that looks like this business. That's the inverse function. You just flip-flop the x's and y's. But visually, it's very easy to check this because we also know that this is going to be, I'm trying to get a line drawn here. This is going to be a diagonal line that flips the graph. Do you see how the green and the blue are perfectly symmetrical? If I had drawn them perfectly symmetrical. That they're perfectly symmetrical across this orange line I wrote in. That orange line is the line y equal to x. That's what it's symmetrical about for inverse functions. Now, there is still a way to find the inverse function for a graph that does not pass the HLT. For example, oh no, it didn't stick. Okay, sorry for that. I got it to stick finally. Okay, so would you agree with me that if we ran the horizontal line test on this parabola, that it would not have an inverse that is a function? Because it fails the horizontal line test. What if we only use this side? If we ignore the blue side, the one side that's blue for me, and I'm like straight up, I'm just going to ignore it for a second, and we only used that half, would that part pass the horizontal line test? Yes. So we can still find a restricted version of a function having an inverse that is a function, as if you know it does not pass the horizontal line test. Here's how we do it algebraically. So let's say we have y equal to x squared minus 1. That's the equation of this line. I'm going to switch the x's and the y's like I did on the first page. And I'm going to solve for y. Add 1 to both sides. How do you get rid of a square? Every time you take the square root of something, what do you have to put in front of it? Plus or minus the square root of x plus 1 equal to y. If we're going to graph this, what we're going to have to do is only use part of instead of both of these curves, meaning we're actually not going to use the positive and the negative version of this square root. We are only going to use the positive version since we only have the positive part of this parabola. So even though you know in your head square root means plus or minus, we restricted our starting, so we restrict our inverse. The inverse for this pink part, the inverse of this function, would just be the positive version, square root of x plus 1. So if we graph this, so we can see what it looks like, we would start off with the coordinate point negative 0, comma, negative 1, which changes to what on my inverse? 0, comma, negative 1 becomes negative 1, comma, 0. The next nice coordinate point I see on this graph is at 1, comma, 0. What does that turn to on mine? 0, comma, 1. The next nice coordinate point I see here is at 2, comma, 3. 3, comma, 2. And then it goes off screen, but I know the next nice coordinate point is 3, comma, what is it? 8. So you would go to 8, comma, 3. And so this sideways half parabola is the inverse of the half of the parabola we were able to actually find an inverse for when we started. Again, we could only use half of the graph because the other half makes it fail the horizontal line test. The part of the parabola I marked off, don't write this down, just watch for a second. This is the part of the parabola I marked off, right? If we were to do the vertical line test right here, would it pass? No, it would only pass the vertical line test if we didn't have this bottom section, which is why we restrict it to begin with, so we'd end up with a function at the end. I knew we were taking the positive side for this one because it specifically told me to use the positive side where x is greater than 0. Oh, yeah, I might not have read that part out loud. But yes, it told you which side to keep. If it wanted the other side, it would say x less than or equal to 0. Thank you for pointing that out. I don't think I drew our attention to that.